Hello, hello. I can put you also in the now and say hello. Okay. Hello, Rishi. I don't know. I think he's not. He's still logging in, probably. Rishi, can you hear me? What? Oh, yeah. Rishi, can you say something? Maybe I was not hearing. We'll give it a few minutes, I guess. No, I think we'll start. I don't know. We'll see. No. Hey, Jupesh. Jupesh, can you hear me?
Yeah, I can hear you.
Oh. We are not able to hear you, I think. Maybe. Hello? Can any of you speak or say something so that I know whether my audio is good?
Can you hear me?
Yes. Yes. Okay. And you can, of course, hear us, right? Yeah. Okay.
Yep.
Good. Good. Okay, so I think we'll wait one more minute, maybe that will be 5 minutes after 3, and then so it's going to be only Rishi and Jupesh. Okay, so let's begin maybe. There is no audience as such from what I can see. So and we have Prachi here in the room. So I can just quickly put the video there. So that's Prachi. And oh, hi Rishi.
Hi.
Okay, so yeah, so maybe what I can request is that you guys could pretend as if you don't know the details and we could have a discussion, so the recording might be useful. So let's presume that the recording is helpful for some audience, if at all we have an audience in that sense. That's something that we could aim for. Okay. So I wanted to ask, raise the point as to, or we had this discussion last time, that if you have a inclined plane, let's say that's an angle theta, and there is a disk or a ring, doesn't matter, some wheel that's rolling, we said it cannot roll unless there is friction. If there was no friction, this will simply slide down. So we would like to see that when friction is asking or friction is acting, what's the motion about? And in particular, we would like to ask, so friction is resisting motion here. I'll do the details a little again. And we are asking what's the work done by friction? What is the, let's say, total work done by the force of friction and let's assume during, so I had to add this fact that during perfect rolling, so it is possible that it could, even while it is rolling, it could slip. So we are saying that it is exactly in contact with the surface in a perfect sense, and that perfect rolling will be defined as, so if you have this line, so if you have a reference line, the angle it rotates, so there is an angle here, so let me call this alpha, and this can be angle theta. So we are saying theta times r, So that's your radius r is equal to the distance it travels along along the incline, right? So that's your distance s. So that's the requirement for a perfect row. In that scenario, we're asking what is the work done by the force of friction. So I'll go over the whole problem. I'm assuming this is addressed to a high school audience, so they might have just come across the Newton's law. So I'll go over the equations and then I'll do the energy formalism and see how this goes through. Or if I have to just give a glimpse of what I am addressing here, usually how you work on this problem is if you're often we get used to preparing for exams and there is a prescription we follow, we will say that let it start from rest. So there is a kinetic energy in the beginning, right? Half mv square. This is the linear kinetic energy. Plus there is a rotational kinetic energy. So it's half I omega square. Hello? We have Euclid. Hello?
Hey,
Can you
Shajesh.
hear us? Yeah. Oh, yes, that's great. Yeah, that's Sammy, I suppose, right?
Yes.
Yeah, okay, correct. Okay, cool. So I was saying we have a audience of reasonable experts here, but let's pretend that this is addressed to a audience who might see the recording in the future. So be critical. It will be nice to hopefully this will be useful. So just to introduce each other, I think Jupesh is my cousin. He has engineering background. He's in Bangalore, works for Adobe, has been with Adobe for quite long. Rishikesh is a professor of physics in BITS Pilani, a very reputed college or university in India. And Euclid, it is Sammy, basically. He's also an electrical engineering by training. He works for Caterpillar in the research division. So he's been a friend for quite some time. Okay, so it's all, and we have Prachi, of course. I should again turn the camera. So that's Prachi again. Okay. Yeah. Okay. So nice thing. Okay. So I was saying that if a disk is rolling, we typically presume that energy is conserved. The typical way we would go is that there is a kinetic energy, linear kinetic energy, and talk about what is linear and rotation in a minute when I go through in detail. There's a rotational kinetic energy. This is all initial plus mgh. Right, so that height will be here. So that's your h. Let's say this is initial. Let's put initial here. This is initial h initial, and this should be the same at the end. So that's half mv final square plus half I omega final square plus mg h final.
It should be true only if the energy is conserved, right? I am being critical.
Correct. Yes, exactly. So yeah, so good. So what Prachi is pointing out, right, this should be true only if energy is conserved. And you would immediately ask, there is a force of friction that seems to be doing work here. In fact, it will be doing negative work here. So what is happening? So that's exactly the question I'm addressing here. So this is how you would proceed. If you say that it starts from rest here, initially it is at rest, and let's say h final, I can choose, I have a choice to choose my origin somewhere. So I make a choice that h final is 0. And this is a choice again that you say this is from rest. And you say that, oh, this is equal to this quantity mass cancels out because there is a mass in the moment of inertia, and you can solve for V final. We will do this in detail. This can be solved, and it gives the right answer, right? It gives the right answer. But then Prachi just now pointed out that that seems to be very odd that it should work, because force, we didn't take care of the work done by the force of friction. That should be, there should have been a work done by force of friction. What happened to that? And that's what I would like to address and talk a little bit more details. This is correct, there is nothing wrong in it, but there are some details we miss in this whole argument, and that's what I want to bring out. It's a sort of a concept. We are saying that certain things that looks, I think Rishi pointed out in one of the conversation that certain things that look simple need not be simple. So we would like to address the details of that. So something like that. Any comments or questions at this point before I proceed? Okay, so how do we address this question? So let's have a simple summary of how do we do Newton's laws. This is a, yes, please. Correct. Yes, yes, he did it. Yeah, so it's sort of a repetition of. Yes. Mhm. Yeah, I just thought it might, since there was a lot of discussion in there, maybe address it, and then we can do something. As we proceed, we will have enough opportunity to talk about other topics. That won't be a problem, I suppose. Okay. Oh, the question was, I think, I'm not sure if you can hear Prachi speaking very well or not, because she doesn't have a mic with her. Yeah, so they couldn't hear. So Prachi was pointing out that, is this a independent way of doing, or is it a continuation of Shankar's talk? So I was saying, yes, Shankar did derive this using Newton's laws. And the only thing I'm going to try to do is the conservation principles, use conservation principle, and just point out what is the work done by the force of friction, and hopefully some discussions will come out which will be useful in general. Okay, so first thing we need in this is that this is not a simple body. There is a rotation and linear motion, translation motion, you say, happening together. So in general, if you have let's say you throw a ball which is not really spherical, there's an elongated ball that is thrown. If you have a center of mass of that object, the center of mass is a special point inside the object, and that point obeys a certain set of equations, and about that center of mass you have an axis. Let's say that's coming out of the board here, but it doesn't have to be. So you can break this whole motion into two motions. So this is, if that makes sense. So there is rotation about that, and this whole motion, so complete motion, can be broken into a linear motion. Linear doesn't mean that it's a straight line. I think strictly it should be translation motion, I suppose. So translation motion plus a rotation about an axis passing through the center of mass. And center of mass, let me say it is this. In general, this axis is not fixed at all in space, but we are doing a simple problem, significantly simpler problem, where you have a wheel that's rotating, the center of mass will be right at the, or let's pretend that the center of mass is, it's a uniform disk. That's for simplicity. That'll be interesting problems if it is not really coinciding with the center, and there will be an interesting motion there. But if it is right at the center, so this point is moving along a straight line, that's the motion I'm talking about, the translation motion. And about this point, you have an axis that is coming out of the board, and about that axis you have rotation motion. So we have rotation plus linear motion. As far as the linear, so sometimes I will also call this linear motion. It's useful. So the linear motion in this case, it is very appropriate, is given by Newton's law. So the motion itself is often useful to represent the motion as acceleration. Velocity is not necessarily the motion. It is the acceleration that's contributing to the motion, and that is helped. So motion of what? Motion of the mass. It could be a distributed mass, but here we are talking about the motion of the mass, but it is the reference point is the center of mass itself, and it is equal to the sum of the forces that's acting on. Slow down. Okay, Prachi says I should slow down. So the translation motion of this object is, when I say motion, I mean the acceleration of the object, and when I say acceleration of the object, I mean the acceleration of the center of mass. This, what I'm writing, is Newton's law. It says that, if I want to write it in slightly different form, this is the motion. It is helped by all the forces that's acting on it. So there could be many forces that acts on it. So we have to identify them. We will do that in a minute. And this helps the motion, and the mass resists the motion. Right? That's Newton's law, if you want. The motion is helped by the vector sum of all the forces that's acting on it, and it is resisted by what we call inertia sometimes, or the mass of the object. It is convenient to write it in this form, and it is always, or it's kind of very pretty much always written in this form. We have to identify the forces that's acting on it. It is a vector sum of all the forces acting on it. So let's identify them. They're usually, at least at the beginning, it's good to have a feel for what are the forces. It's always only after some experience you learn about what kind of forces are acting on it. It turns out that typically in the beginning, there are only about 4 or 5 forces you talk about. One is the gravitational force, and how you look for gravitational force is that, are you close to any other object? If you're close to any other object, there will be a gravitational force. It depends anything that has a mass in general. And we are always next to this Earth, and that's a gravitational force from the Earth. It acts exactly towards the center of the Earth, and when we are right next to Earth, it is almost like saying that it is perpendicular to the surface. So that's mg. So that's, with some experience, you say that, oh, that's one of the forces that acts on it. The other is the surface itself. If not for the surface, the tendency for the wheel or any object will be to go towards the center of Earth, but the surface pushes it off. So it is pretty much one object not trying to penetrate into the other. It's a property of a solid object. In this case, we are also saying this is rigid. By that, for our purposes, it is sufficient to say that it's a proper solid. It doesn't deform in any form. That's what is typically, or you can make it more rigorous and say that it's a rigid body. The 2 points inside the body doesn't, the distance between them doesn't change. So the surface doesn't let it go inside, and that exerts a normal force, and it is exerted. So in this case, we have to worry about where the forces are exerted, and for ideal purposes here we will be pretty much ideal and say that the point of contact is a single point. I think it was a good discussion raised by Rishi, I think in one of the discussions we had in these last few weeks, that he pointed out that in real scenarios, this point of contact is not a single point at all. There is a small extension there, so it presses on it, and that allows the stress or the normal force to be looked in a little more detail. But here we are in the ideal scenario where the contact is really a single point, so that we don't, at least hopefully we don't have to worry about the complications that came up. But it is true that in real life we will always have that. But this is an academic exercise in a sense, and still we'll be able to point out some interesting things, I suppose. So the normal force acts at this point, and since it's perpendicular, it will pass through the center of the disk or wheel at this point. So that's a vector. That's your vector. And what other forces act on it? So usually you look for a string, or that's the force of tension, or is someone else pushing or pulling on it? It seems like it's just rolling, so mg normal force. And if there is friction, it will try to resist this motion, and that's the way we look at it, because there is a tendency for this to accelerate downward. If imagine again, if it was frictionless, if it will just accelerate downward. So there must be some resistance to that. So intuitively, you think that there is a force of friction. Yes, please. So Prachi has a question. Yeah.
So the need here is that just because it's like that, it has a tendency to slide down.
Slide down, correct.
There should be a frictional force opposite it.
Correct. So
But it's not sliding on it. It's like right end, it's the right amount of frictional force which is sitting there. So that frictional force, I mean, we say it is doing friction, but I mean, what exactly it is?
okay. So the question here, Prachi is pointing out is, let me try to word it again. So she's saying friction is opposing the sliding motion, and you use the word rolling friction. And what exactly is that? Maybe I'll put it, I'll give the mic to you.
I'll say it again. The point here is that normally frictional force is static when there is no relative motion between the two surfaces. And it is sliding when there is relative motion between the two surfaces. The point here is that the frictional force has to. I'm sorry.
I think it was.
Yeah, so my thing was that like the frictional force has to act there because it has to resist the tendency of sliding down the incline. And that frictional force has to go in the opposite direction. That is also true. But honestly, there is no relative motion between the two surfaces.
No.
They are not, this is a perfect rolling scenario. This frictional force is exactly something. It is not having a sliding motion. So we call it, okay, it is a rolling friction, but exactly what it is, I mean, I don't understand.
I think it is.
I understand, see, I understand static, I understand static, I understand sliding. I just don't understand rolling, because rolling coefficient of friction is actually in terms very tiny, like it's like 0.0005 kind of thing.
The way I would, I think Rishi pointed this out in the discussion more clearly last time, but the way I see it is that at that point of contact, there is only, this is really at rest.
So is it static?
Yes, so it's coefficient of static friction, but not necessarily mu s n, because mu s n is the maximum value. Yeah. It is not mu s at all because it's less than that. That's all. We just need that some number there.
You cannot work at a coefficient of friction at starting. That's like that. My understanding is that that coefficient of friction is not coefficient of static friction.
No, we want to address this. Maybe Rishi, you can add on to that. I
Actually,
think.
Actually, right now, the small f or capital F subscript small f is just that. You cannot write it in terms of mu times n or something. It is some
Correct.
unknown force which we don't know.
Yeah,
It is the force which is responsible for.
I agree. But then what's the confusion? I would say that this is the, okay, force of friction. This is static, remember, relative to this point, this is really static. So force of friction is less than or equal to mu s n. And you can consider a scenario that's, I think that's what I was trying to address there in that a small paragraph I wrote in the WhatsApp group, that if you were to keep increasing this angle, there will be a point when this will start sliding or slipping. And that is when this will equal that. So it is just exactly the coefficient of static friction, except in this case, since it is less, usually you would say that I don't even know it unless I have an external force acting on it and it equates to that. Here we will be able to discuss it because it will give me. Yeah.
So is it okay to say that this is force of static friction?
We'll
And
have to get close.
I think everybody can hear me, right now. So my point is that, like, I mean, we can say that this is force of static friction, as you are saying, right? This is force of static friction, but it is anything which is way lower than probably mu s n, right?
Close to mu s and also if
Yeah,
you increase
it will not be equal, because if it is equal, after that sliding will occur. Okay, I completely agree with that. Then what is the difference between this force and the rolling friction force?
It's just rolling, I suppose. I think I personally believe that there is no need to bring in the idea of rolling friction. This is just the static friction.
So maybe Rishi, you might be able to help out much. You have taught the statics and dynamics for the engineers, right?
So, Pati, I think when we talk about this pure academic physics, I don't think there is any real mention of rolling friction in the textbook of physics. Now, when you teach to engineers, then the force of friction and the rolling is slightly more complicated, as I had told last time. So what happens is that, if you look at if you zoom into the point of contact between the disk and the flat surface, okay. In fact, it's not exactly like what I told last time. Last time I said that the normal reaction is slightly displaced and vertical, but actually speaking, there is a kind of a curvature at the point of contact between the disk and the surface, and the normal reaction is not vertical, neither vertical nor horizontal. It is pointing at some angle, okay, and it has the horizontal component provides one friction, and the horizontal component of the normal reaction adds to the friction, and the normal vertical component provides the torque which will reduce the rolling. So it is only when there is a finite contact and the normal from the front point is making a angle which is neither vertical nor horizontal. That's when actually we have to worry about to what extent it will modify, because the modification of the coefficient of friction will be non-trivial when there is a finite. See, there are two things. A, there is a finite surface into contact and the shape is not flat. Okay. And that's why the modification of the coefficient of friction will be non-trivial. Okay.
Yes, I get the point. So the point
Yeah.
here is that if there is a deformation of the surface,
Yeah,
in that situation, there will be loss of energy, and that frictional force which is causing the loss of energy is what probably engineers are terming as friction, rolling friction, maybe?
Again, it's slightly tricky here, Prachi. Loss of energy is there, but it is not because there is no sliding here. Okay, the energy is lost because the normal reaction is normal reaction which is displaced from mg is this is normal reaction, this is mg going down and slightly forward, and this n is providing a torque in the opposite direction. Okay,
I'm getting.
which is absent
I'm
when you have a perfect rolling with a single point of contact. Here also it's a perfect rolling. Okay, even in this context, when you have a pneumatic tires, there is still perfect rolling going on because there is no slipping. Okay, but
Yeah,
there is
this
a
one I
counter
can-
torque.
This one I can understand. My problem is that there is a term used in engineering, mechanics, and that is called rolling friction, and the coefficient of it is mostly considered close to zero, but there is a tiny friction what is called coefficient of rolling friction. So there is something which is coined in engineering, and that is what like keeps confusing me all the time, because I do
Yeah.
understand that this is
As I said, Prachi, as I said, it's that coefficient of rolling friction factors in this exact contact and the angle that normal reaction, makes with the vertical. It's not exactly normal reaction, is not vertical, it's making an angle. And that's why there is an additional, there is a friction force and there is a horizontal component of normal reaction which adds to it. And there is an effective resistance which is taken care of by an effective coefficient.
Yeah, I mean, like it's more or less like something that yeah, more or less I get it. It's just like it keeps confusing me all the time. Like when we use the terminology of rolling friction
Okay,
in
so-
engineering.
The long and short of it is, Prachi, when you are talking about this single point of contact, then it doesn't matter. I mean, what Shajesh is doing is
Exactly.
perfectly fine. It doesn't really matter.
Exactly. Yeah. It is
Yeah,
only for the default that we have.
Yes, yes. It doesn't
Yeah.
matter here.
Yeah, I want to add.
Yes, Simon?
I want to add
Yes.
I want to add a funny comment, which I agree with what is being discussed. If we imagine the incline as an intelligent being, without being, it won't know the difference between a rolling object or a point mass going down with the same force of friction. For the incline, both cases will be identical. Won't know the difference. So the incline, when they are gonna put the force of friction, it is going to see the same effect, whether it's a rolling object or a point mass at the point of contact going down.
Yeah.
Yeah, in
Yeah, I
both,
think basically he's saying the same as this, correct?
which
But
is
I
good.
think
Which is going to be dynamic. If you want to calculate the coefficient of friction, is going to be the dynamic one because the point of contact is moving.
no, right? Because if it is coefficient of kinetic friction, then you will have an exact number there, but it is not, like it is less. So I would disagree that it is coefficient of kinetic friction. It is a single point of contact there.
It's going to be
And
kinetic.
then at that, and it is not moving, correct? With respect to this point, how do you say this?
Yeah. And the point of contact is moving down, right, with time. Same as
relatively, I think if I tell this like, so suppose we have this point is moving with velocity v, this point is moving with velocity 2 times v plus omega r, which is 2 times v, and this point here is 0, right? So something like this. So as you go all the way down here, its relative velocity is 0 with respect to an observer sitting right next to it on the ground. So in that sense, it is static, and so it satisfies this.
But
Am I okay with that?
what about an observer who is sitting at the at certain location that is not moving with the point of contact?
Good point. And actually, this immediately raises the question that this point will have to be accelerating, right? So every time you're jumping into an inertial frame. So yeah.
Yeah, so
Can
I think
can you repeat the question, please?
Yeah, please. Yeah. Oh, you wanted to see, is that what you said?
No, can you, sorry, I didn't, what is the question?
Oh, I think Sammy is asking that it should be, this force of friction will be a force of kinetic friction, because he says this is, if you take this as a point object that is moving with respect to this incline, so this force of friction will be a force of kinetic friction. And I am trying to point out that it is actually at this point it is at rest. But then Sammy is pointing out that that's okay, but what about any other point of frame? Like there is another reference frame and it should be okay to use that. And we also have this challenge here that if we are really going right next to this point, we have to keep jumping from one frame to the other. And in that sense, maybe we are not really in an inertial frame in a strict sense.
No,
At every
this point
instant,
will be
probably
at
we are.
rest. This point is at rest.
This point is at rest, yes.
Yes. It is accelerating, but at rest.
Local inertial frame, yeah.
It is accelerating, but at rest.
yeah, it is at rest with respect to an observer moving with that point.
Yeah, it is instantaneous center for zero velocity. So it is like instantaneously at rest. But the next moment it is not.
So you have to jump from one inertial frame
Yeah, so if you want to apply whatever you do in this frame of reference, you have to consider the other frame of reference in which it is another IC. But then the point is in space as moved.
So, okay, good question. So, okay, so again, the point being raised is that I am proposing that this point is at rest with respect to a point instantaneously in contact with that. And at the next instant, it will be at, but it's a different velocity. So it seems like you're jumping from one local inertial frame to another local inertial frame, which is not, we know we use that in some other context, but not usually. I didn't realize that we were really doing that here.
No, but we are formulating this equation of motion with respect to some fixed point, which is not that. We are formulating this equation of.
Tell that again, Rishi.
I'm saying we are formulating our F equals ma here in a frame which is not this point of contact. Okay. Suppose you have a triangular ramp here and you use this fixed point at this left-hand corner. When you are writing your F equals ma here, this F equals ma refers not to this point of contact, but some fixed point which is not this.
Actually,
okay.
Yeah, I agree. We are not really with respect to this point.
Exactly.
I can have an observer here. It's just that instantaneously with if this is velocity v, this will always be zero velocity, correct?
Yep, yep, yep. The trajectory traced by any point on the rim of the wheel is a cycloid. And and this will be the bottommost point, and it will be at rest. And you see here, actually there is there are two things, you know. I mean, he has written the Newton's second law here, but he will also write the torque equation, right, Shajesh?
Yes, I will write the other equation also.
And the torque equation, I suppose, you will write about the center of mass. Am I right, Shajesh?
Correct. Yes, yes,
Now,
I will write
now
it.
it turns out that the center of mass is accelerating, okay?
Correct.
But it turns out that in general, if you are writing your torque equation about a point which is accelerating, okay?
Yeah.
Then there is an extra term that you have to take into account called pseudo torque. Okay. But there is an exemption. If that point about which you are calculating the torque happens to be center of mass, then that pseudo torque term vanishes. So center of mass is a special point. But suppose
Correct.
nothing stops you from evaluating torque about this point of contact. Okay.
Correct.
In which case, it's an accelerating point. Although it is at rest, but it is accelerating. Okay. Rest does not mean that not accelerating, right? So it is accelerating,
Yes,
and
that's
you
right.
have to factor in that term. But again, it turns out that for a wheel rolling down the incline, that term will not, the pseudo torque turns out to be zero. So people don't factor in the pseudo torque, but they get lucky without knowing that the pseudo torque happens to be zero in
Cool.
this particular case.
Yeah, you brought this out last time.
If you want, next time I can show you that, you know, we can formulate the torque of a torque on a rigid body about an arbitrary point, okay, which could be even accelerating, and obtain the general torque equation, and then see how these all special cases come about. And we can do a given problem by finding torque about the center of mass, torque about a fixed point, and torque about a point which is accelerating, and see that how the pseudo torque term actually comes into play.
Yeah, I don't mind doing that.
And some
here,
other
but-
point, some other point,
Yeah,
some
yeah,
other
yeah,
time we
you
can
should.
do it.
Yeah. So, Sammy, does that address your question?
Yeah. I think you're, I mean, in a way, I mean, in a regular linear motion, we don't know what is the friction, but we know the N and we know the friction coefficient. And then we calculate the friction. In this motion, we don't know the coefficient, but we know N, and we should be able to calculate F.
Yes.
And then we should be able to calculate the ratio between F and N, and then we can call it whatever we want.
Yeah, but this is less than or equal to, so we cannot really say that's mu s, right?
Right, yeah, which is gonna, but this is like yeah, I mean, it is, it's, yeah, exactly. There is inequality that make the comparison different, but it is gonna also depend on the mass and also a few other factors. So we can continue, and then you are gonna calculate probably the force as well, the friction force down the line.
Yes.
Okay.
I suspect that the mass will cancel out. So
yeah,
and it will be just geometry dependent kind of in this case. Yeah.
Okay.
So Prachi is not very satisfied still.
No, that's okay. That is, I mean, there are different interpretations that are coming into picture, and the point is, like, in one case it looks like the next moment this point is going to slide or go in different place, And in another case, it looks like it is just a static. So yeah, I don't know, like, yeah, it just bothers me, like the nomenclature of what this friction is actually.
But I think I feel Rishi pointed it out clearly, and I think I agree that if I am making the assumption that this is really rigid, ideally rigid, and it's in contact with only one point, we don't have to worry about that. Like this is just the static friction that's acting. So can I proceed?
Not a disc, suppose this is a rim, and I cut the rim and flatten it out. Are you trying to say that this point, like this is just lying static? None of the points are moving with respect to any point?
Oh, no, that's not what I'm saying.
Anyway, let's move.
No, that's not what I'm saying. Like that, no, that's a big extension you made. I'm not saying that this is equivalent to opening this. If it was a ring, opening this and keeping it flat, that's the same motion. No, that's not the point. In fact, it will be different force in that case.
It's actually a function of the geometry. You know, the one point of contact is possible only when you have a perfectly circular geometry and no deformation, perfect rigid bodies rolling over each other.
Yeah, so this is a perfect rolling has to come in, and all that it plays a role.
That's why it's all a function of the moment of inertia, the distribution of mass.
Yeah. Okay, so hopefully with not very satisfied audience, I suppose I proceed. In this case, there are 3 forces acting, and I have 10 minutes remaining. So let me quickly do this. So this is mg plus the normal force plus the force of friction. So that's your 3 forces. If we use this equation in the vector form, we can proceed and get some information in, at least if we are thinking that everything is happening in a plane, we get information, 2 equations. But there is one more equation, as I said, there is rotation about an axis passing through the center of mass, and this is the axis passing through this point, and we are saying that center of mass is really at the center of this geometry. And it's interesting, if you can imagine, like if the center of mass was not really at the center, then it is like a wheel that is sometimes you get a blunt wheel, and then you think of a motion of a wheel around that. So it's not really smooth in the, yeah, it will or not only skip, like it's not a, it bumps, right? I mean, so it's not a clean motion there. So it's surely complicated there, but I'm taking very simple, the simplest motion, I think, by including rolling motion, is that you keep it everything center, or the axis is always pointing in the same direction. So it's basically one-dimensional motion in that case. There is only one angle that describes the motion, and the acceleration, rotational acceleration of that angle, like this is how angle is changing, and we are saying that there is only one dimension, because so there is this point here, something is rotating about that, and we said that's angle theta. How is this angle changing? That's the only information we need about when we are saying that this object or this wheel is moving about an axis that's pointing in the same direction. And I said alpha. Let me not write alpha here, because I used alpha for the angle there. So let me say this is second derivative of theta with respect to t. This is second derivative of x, and that's now we ask, this is the acceleration of the angle if you want, and this will have torques, right? So there is a torque. Each of this force causes a torque. It should be a vector equation, but I have put everything in one direction, so I don't have to worry about vectors. It's only having a plus or a minus. So there is a torque with respect to the normal force plus the torque due to the friction. If they create torques, each of this will create a torque. And as I said, there will be, in this case, mass was the resistance to motion or the inertia we call. So now we have a rotational inertia, and it is not just the mass, it depends on mass and the radius and the geometry of the object itself. So that's what is moment of inertia. So that's I, and in general, for simple objects like the ones we are doing, this is usually m, the mass of the object, times the radius squared. If you can define a radius, if we have a ring or a disk, that's the two situations we can consider here for our discussion. But in general, it might not be very easy to define a radius of an object, right? So if we have a radius, and this often comes out as a number, right? That number itself is kind of interesting how we can get that number. And let's call that number P here. Like P is, if it is a circle, then it is 1. If it is a disk, that is uniform disk, then it is half. And if it was a spherical object, then it is 2 by 5. Like so that's your two equations, correct? We can use these two equations and solve for everything you need to know about this problem. And that was what was done by Shankar in his lecture 2 weeks back. Like, and he went through it in detail. We had good number of discussions in there. Here, I want to do the energy formalism. Basically, what you do is that start from this equation and start from the first equation and multiply it by the displacement of the object, let's say dr, and take a dot product of this whole equation with that, and you go from point 1 to point 2. You start from our initial, which is a certain point here, starting from rest, and you go there. In that form, this takes the form of kinetic energy. This takes the form of potential energy, but you have to move it to the left to have that interpretation. It's just basically a sign change. So the work done by this gravity is interpreted as potential energy because it depends only on the initial and final point. Normal force does not do any work because always the displacement is along the incline. Normal force is always perpendicular to that. This dot product does not contribute. And it seems like the force of friction surely contributes to this this energy relation. So what we can expect to write is, so if I switch my board now, so you can still see part of this equation. So what we will have is that kinetic energy. So there's a change in kinetic energy. So K final minus K initial, that's what it means, where K is half mv squared. So that's my energy associated with linear motion plus, so that's equal to the work done by the gravity. That's a change in potential energy. So it's a work done is the negative, is interpreted as negative change in potential energy. Change because the potential energy depends only on the final and inertial or final and initial points. It's a conservative force, and there is no work done by the normal force, that's 0. And there is a work done by the friction, correct? In fact, it is negative F. So this is negative force of friction. I'm assuming that force of friction does not change with WF, but I was going to write that as dotted with S. Let me write W, force of friction. Reasonable? And this is plus now then, right? I don't know what that is because I'm in proton. And that is what was the question being raised in the title of the talk. What about this? Like, this should change that prescription, and we should get some laws of energy. Let me say this is a linear motion, right? But the idea here is that that's not the complete story. Clearly, we haven't included the rotational kinetic energy at all. We have to go back and address the rotational motion here. Let me show that again. So we have to take care of this equation, do the same thing, but this time we do the rotational analog. We're talking about the rotational displacement. So I do the same thing. Since we are working with respect to an axis that is constant in space, there is only one dimension. So it is just d theta. In general, this should be a vector d theta and the torque d theta, but in our simplified configuration, we simply have an integral over theta, and you start from initial and theta initial and theta final. Again, in this case, now gravity does not contribute to any torque. This time I'm saying I'm at the center of mass is my reference. Rishikesh pointed out some subtleties. If you were to use any other point, that should be, we should address that here sometime in the future. But if I proceed, so this is acting right at the point of at the center of mass itself. So there is no moment like the radius of like there is no distance from the axis at all. So it doesn't contribute to any torque. So this is 0. The normal force is 0 because it is passing through the center. That does not contribute either. So that's equal to 0. But this time, the force of friction does contribute to the torque. In fact, we see that it helps the rotational motion. So the friction is helping the rotational motion. It is resisting the linear motion. And if I were to put this together, this comes out as exactly like we had earlier. So this is change in kinetic energy. This is from the rotational part, or where I should point out KL was half mv square, and the rotational kinetic energy is half I omega square. So there's always this one-to-one correspondence. Mass is, this is the rotational inertia, mass is the inertia for linear motion. This is linear velocity, and this is the angular velocity. In this case, there is no, gravity does not do any rotational work. So that's 0. Normal force does not do any rotational work, but this time you do the force of friction does do a rotational work. So let's differentiate between these two. Let me call this the linear work done by the force of friction in the linear motion, and this is the work done by the force of friction contributing to the rotational motion. And as intuitively we can see, this contributes to positive work because it's helping with the motion, and this contributes to a negative work because it's resisting the linear motion. And together, if you were to add, you get change in kinetic energy plus change in kinetic energy due to linear motion and rotation motion, plus the change in potential energy. This is what we began with, and that's equal to the work done by the force of friction in the linear case plus the work done by the force of friction in the rotational case. And the nice part is that this really comes out to be 0. Let's really quickly look at that. So that's the work done by the force of friction in linear motion is simply force of friction dotted with dr. You're starting from initial point to final point. You're going on an incline. This is in the backward direction. And is there an easy way to argue that this is really constant so that I can bring it out? Help. So that's force of friction, and that's dr, right? So I would like to argue that this is constant during the motion. So this really comes out and because there is cosine of 180, that is minus f times the distance d travel, let's say s. Right? This is rf minus r initial, but this requires the presumption that this is actually a constant during the motion, and that has to come independently. And
When we
here?
found out the acceleration,
Yes,
it turned out to be
So that-
constant, right?
correct. No, I know
So
that
now-
it will be a constant, yeah,
No,
but
so once your
at this,
acceleration is constant, your mg is sine theta is constant. So f is
Ah.
nothing but the, sum or difference of these two. So it has
Correct.
to be constant.
yeah, so you can say this is mg sine theta
Yes, minus f.
plus the normal plus force of minus force of friction,
Is equal to ma.
and that's equal to ma. But we don't know a yet, right? So that we have
we
to go into
calculated
the
a
next.
last time. We calculated
Yeah,
a in
yeah, we
Shankar's
calculated a last time. Yeah. So we have to, I guess, use the information from solving the linear or the solving the actual Newton's law. We cannot argue it right here. So I've used the fact that force of friction is a constant, right? Which has to be derived independently using Newton's laws of motion in the linear case. So in that sense, it's not complete argument here. Also, the work done by the force of friction in the rotational case is equal to, now we are talking about the torque and times d theta. So this is going from theta initial to theta final. The torque due to friction in this case, so this is the rotational motion here happening. So that's perpendicular to the radial vector. So that's just force of friction times radius r. Again, if it is a constant, so this comes out to be plus the force of friction times the radius r times the angle theta. So the change in angle theta. So this is the total angle, it goes from 0 to a finite value of theta, and this is the distance it goes from 0 to s. And if it is perfectly rolling, these two quantities are the same, right? S is exactly equal to r theta. That cancels out. And if it is perfectly rolling, we don't have to worry about this. That's really equal to 0. And that's how we calculate the velocity. So the main point I was trying to point out is that yes, the work done by force of friction is 0, but that's because of this fine cancellation which happens during perfect rolling, and which is the assumption we are making. So with that, I think I will close my discussion here. So any comments or? Oh, hold on.
The total work done by the force of friction will be the linear as well as rotational, and that total is 0. Independently, neither linear is 0 nor the rotational is 0.
So the linear work, it is resisting, as intuitively we would say. So you do lose that, technically you do lose, but then you gain in the rotational part. So it is slowing down. If it was sliding, it will be slower than the sliding scenario. So in that sense, it is resisting it, but then you gain in the rotational part. So overall it is 0. So technically the work done by is exactly 0. So that's what I wanted to highlight in this configuration. Yes. Yes, Rishi.
Yeah. So I mean, as you know, it's this problem beautifully illustrates that the function of friction in a pure rolling under, I mean, acceleration is to convert the translational kinetic energy to rotational kinetic energy. That's it. It just does.
Exactly.
It just does the, you know, your reduction in translational kinetic energy, and that is exactly, gained in the rotational part. So where does rotational part come from? It is coming from the reduction in translational. Okay. You will
Correct,
see,
correct.
that the gain and reduction is exactly same between rotational and kinetic.
Correct.
And that's what the work done by the
Yeah.
friction is. Okay.
Yeah, so this is balanced. So you're just splitting. Yeah, you're taking something from this and creating
Exactly. It's just redistributing. The friction does that job of distributing. Now there's a physical way to argue that F has to be constant. Okay.
Yeah.
I just thought about it. I don't know. I mean, please see whether it makes sense or not. So suppose you were in a, to begin with, you were in a perfect rolling condition. Okay. Which means your acceleration, the translational acceleration and angular acceleration are related, right? A is R alpha.
Correct. Yeah.
Okay. Now assume that the force of friction increases. Suppose it's not staying constant. Suppose it increases, right?
Yeah.
So look at your
Yes, good.
translational equation of motion. What will happen? It will end up reducing acceleration, right?
Yes, in
Small
that
a
case, this will increase and this will decrease, and you cannot have that.
So now what will happen is that if F increases, it will reduce
Yes.
small a, that is translational acceleration, but an
Yes.
increase in F would increase alpha.
Correct. So they
Right.
then there will be a contradiction that this
Exactly.
is a perfect rolling. That's a beautiful one. Yeah, good one. Yeah, I agree. I agree. That's a good. That's a really nice argument. Yeah, yeah, yeah.
So you
Clear.
cannot maintain this condition of A equals R alpha.
Yeah.
If either F increases or decreases, either way. It will lead to a
Yeah. So
complete
this.
decrease in the perfect rolling.
Yeah. So this is an argument for why F should be a constant, because if it's not a constant, it will not be able to help both in helping the linear acceleration.
One way, other will go other way. A will decrease, alpha will increase. Or alpha will decrease, A will increase. And that will screw this relation. Sorry, that will spoil this relation.
I can again come back to force of friction being the rolling friction, which is actually mu times some normal force, where it is like in engineering, it is literally equal to some coefficient of friction times the normal force. The rolling friction force is a constant quantity.
Just a minute. So, Shajesh, can you open this page, rolling resistance on Wikipedia?
Okay, give me a minute. Let's see. I can. Let's see. Give me a second.
Rolling resistance in Wikipedia.
Rolling resistance, is it?
Hmm.
Oh, I should share the screen, I suppose. So that. Is this visible at this point?
Yeah, very clearly.
Rolling resistance, right?
Wikipedia, right? Wikipedia.
Wikipedia.
Yeah.
Okay. Help
Read
me.
this first few lines.
Oh, read the first few lines. Okay. Rolling resistance, sometimes called rolling friction or rolling drag, is a force resisting the motion when a body rolls on a surface. It is mainly caused by non-elastic effects. So, but we are not allowing non-elastic.
Exactly, that's what I'm saying. Exactly. That is not all the energy needed for deformation or movement of the wheel is recovered when the pressure is removed. The two forms of these are hysteresis losses and permanent plastic deformation of the object.
Yeah, but we are not allowing any of this because we are saying this is really ideally rigid.
You have to worry about it when you look at the picture here. So
look at this the figure 1, right? Yeah.
Yeah. So now you see, suppose this body is moving to the left, okay, and the normal reaction, as I was telling, is making an angle, right? This R is a reaction force. It is not exactly vertical. So it has a vertical component.
Right.
A, it is not exactly below the center of mass, and B, it's not vertical. So it has a horizontal component, which will add to the friction, and
Help.
it has a, no, it will not help, it will resist. And there's a vertical component which will provide a counter torque to the rolling.
Yeah, rolling it will resist, I suppose, and
Yes, the torque due to
need
R,
more linear
it
motion.
will have a small lever arm. Okay, very small lever arm from the center of mass, and that's why that will act in the counterclockwise. So if the wheel is, it will basically act in the opposite direction of rolling, and it will slow the wheel down. And basically, what happens is that the forces of the contact forces between the wheel and the surface, if they are perfectly elastic forces, then there is no loss. But the inelastic contact forces, where upon the depression, the pressure, when the pressure is removed, it's not fully recovered, and that's why there are hysteresis losses. So you worry about it in these situations.
Yeah.
And
But
it is analogous to sliding friction.
Complete. Yeah. Go ahead.
So it doesn't apply to our case at all in a perfect rolling.
Exactly, because we escape it completely by just one sentence that it is completely rigid and ideal and
Exactly.
perfectly meeting at one point. Yeah. So we
Because,
escape
I've
the
solved
whole
a large
thing.
number of
It is
problems
completely
about this.
unrealistic. I give it to Prachi that yes, it is not realistic, but I'm doing an academic exercise. Here, hold on.
And that's the reason, Shajesh, that's the reason that it is spoken of in engineering context. Where they are not doing academic exercise, they have to design cars and wheels, and which will be in contact, physical contact with the surface, and there will be these issues,
Yes.
That's why you will not find this discussed in even Helder-Resnick or even Klapner, for that matter, even Klapner or French.
Yeah, agreed. Yeah, so I think good point. Yeah. Any other comments?
Okay, Shajesh.
Yes, please. Okay.
You dotted dr, right, with force f dot dr and defined work.
Oh yes. Okay, give me a second. I think I should change my camera. Yeah, go ahead. F dotted with dr. Yes.
Yeah. Now, I mean, as a +2 student, I will worry about this, that you have a set of vectors here.
Yeah.
Forces, and then your displacement, infinitesimal displacement dr is also a vector.
Yeah.
And I know that vectors can be combined in two ways. They can be crossed or dotted. So what physical arguments would you give for not crossing here and dotting? I mean, you might say that, okay, you are defining word, but a priori, what reasons do you have to dot and not cross here?
Yeah. So I typically interpret this in the following way. Like, so I think your question is, why is the work done? Let's say the integral is not crucial. So we have force along the displacement, right? So let's say this is D, correct? So this is the displacement D. Let's say an object M is being moved in that direction, and we have a force F acting in not necessarily in the same direction as the displacement. And the dot product has this feature that it is the component projection of this force along the displacement. That's the interpretation of a dot product. So we are saying break this force into two. Like typically we do it in the X and Y direction. Now we are breaking this along the displacement and perpendicular to the displacement. That break is always possible, right? And here the claim we are making is that this does not contribute to motion in this direction, right? This force is a constraint in the sense that something has to cancel that. That's the need for that force, but this is the only quantity that is providing the motion. Is that a satisfactory Yes.
Um,
Is that what you
I mean-
had in mind?
it did not cancel with anything. I mean, it would cancel if it is moving on a rigid surface, but we can define work done in general, and there did not be any cancellation with a vertical force. So why would I not define work done as a vertical component, then why do I have to define it as a horizontal or the component along the motion?
Yeah, I don't know. I think the cross product will provide the rotation. So
No. So isn't it true that, okay, if there is a force component here, there has to be another force here, like the motion is in a certain direction. If there are forces, all the other forces has to cancel. That's a constraint, right? If we, like typically in the Lagrangian system, you would say this is the constraint equation. So
No, but
here in
I'm
this
saying-
case, it's a normal force. Here it's a normal force that's doing that job. But
I can
so your
I
point
can throw
is-
a stone. I can throw a stone, and it's moving in the air. And of course, we can still
yeah,
talk
in
about
that
the
case,
work done. We can still talk about the work done, right?
yeah, good point.
So-
Hold on.
We can still talk about the work done, or the motion of planets, in elliptical orbits. We can still talk about the work done. And there's no as such. There is nothing
Yeah, good
constraining.
point. Yeah, good point. Displacement. Yeah, good point. So
Whatever you are describing, like whatever is the component of the force assisting the motion. That's what we
yeah,
said.
there is no.
Other than include something, but you're not interested in defining it.
No, but there won't be any work. Okay, help me here. Okay, I think the point Rishi is making is that you have, this is the motion, the displacement, the tiny displacement is dr here, correct? And there is mg here, right? So
Yeah.
it is not, so the force is not in the direction of motion at all. But then it doesn't do any work in that direction either. Oh, so, but then that's a wrong argument I was giving, that, yeah, it's the motion along the direction of the motion. Yeah, good point. So, yeah, I don't know. So help me here. So, okay, so your point is mg. Why is it, how would you motivate the work
Yeah,
done to be
exactly
a dot
it's a
product?
scalar product of the force and the displacement.
Yeah, so why would you do that?
See, I don't know. I mean, the way I look at it is that, I mean, we have to understand what is the relation between the dynamical.
Rishi,
Ah.
may I say something again? Like why
Yeah,
that
yeah.
argument is not valid? That what component of mg is actually assisting the displacement? What component of mg is actually assisting the displacement in that tangent direction? That should define. I'm defining work here, right? Well, in motion, I am only worried about the displacement which is tangential to the path. So I'm saying that what component of the mg is actually supporting the motion in that direction? I mean, it will change the velocity, of course, but that's a different story. The other component I'm not interested in, because and this is what the defining relation of work done is, right? I'm defining that
Yeah,
a
defining,
force
but
is.
see, why is that? I mean, why is that definition physical?
Yeah. So I think in Prachi, what you're saying, if I were to break this into two, right, there is an mg and there is this force, right? Mg perp. But it is not really clear why this will not contribute to motion. Like, we know that it doesn't contribute, but I'm just saying, or actually in this case it does, right? This actually contributes.
No, it does contribute in the sense that it, of course, changes the direction.
Yeah,
It does
yeah.
change the direction. The actual motion is I mean, it's not independent of the dynamical consequence of the.
You are answering your thing again, like yourself. The point is the perpendicular component is assisting in the change in direction, which is related with the rotation about something. While the component which is along the tangent line is actually helping in the displacement or changing the acceleration. So it's like, I mean, I will be defining in mechanics two quantities, right? I will define torque and I will define work done. And both of those component has like some physical meaning associated with it. So work done is like what is actually making the displacement, linear displacement, if you may ask.
Yeah, but I'm saying that, ultimately, both these components are important. I mean, and why is it that the force in the direction of displacement acquires a physical character in the form of work done?
Yeah. I think I see the point. Yeah.
So actually, I don't know, but I mean, so we have to understand that what is the relation between the dynamical equation of motion perspective and the energy perspective. Okay.
Yeah, like basically this is the point, right? Like the one which is along the direction of the tangent or the displacement is a scalar quantity. You define it as something. Another one which is perpendicular to the direction of the displacement gives you a vector quantity. You define it as torque. So there is like, I mean,
there is a physical way of motivating this.
So the question you're raising is there a physical way of motivating it? Correct?
Yeah.
Yeah.
This always bothered me.
I mean, no, good point.
We do not know a priori, we have to invoke these concepts in the first place. Now, you see, so I mean, so what is the relation between the energy perspective and the equation of motion? Of course, it's when you integrate your equation of motion once, the energy is basically the constant of integration, right? The first integral of motion.
Yes.
So now if you write, say F equals, so basically, the question is, what does a force do in space and in time? So if you have F equals dP by dt or F equals ma, so the simplest thing that you can do is do a time integral of force.
Correct.
F dt. And that, of course, just gives you the change in momentum, the impulse, right?
That's change in momentum, yeah.
Yes, that's just the change in momentum. If you happen to know F as a function of time, okay. The point is that you can solve your second order differential equation of Newton's differential equation, F equals ma, if you know F as a function of time, right?
Yeah, let's say that we.
But very often you don't know F as a function of time. Often what you know is F as a function of position, like the gravitational force or the spring force or Coulomb force. So even the in-principle task of solving your equations of motion, we just say that integrate it twice with respect to time and obtain your R. But for that, for you to be able to integrate F as a function of time, you should know F as a function of time, right? But now, if you know F as a function of R, how can you get around this?
Rishi, that is how you introduce the definition of work done, right? Like if you do not know the function, like if your force is changing from position to position, you can define work done as something, right? This is how you introduce the concept of work done, right?
This is not how I introduce the work done.
Like you will have to say that you are not interested in how it is changing with time. You are interested in how it is changing in space from one location to another location. Yeah. This is how you introduce the concept of work done, right?
Yeah, but now, so now when you do this space integral, okay, so you write your dx as some v dt, and you do your one. I mean, you start with a one-dimensional case, and write your, you multiply it by dx on both the sides, and write dx as v dt, and your LHS becomes the kinetic energy. When you integrate ma, it becomes a kinetic energy, right? if you
So
integrate,
can I do this? So let's do this, okay?
Hmm.
So you're saying, let's have a,
yeah, you write F equals MA, write a one-dimensional case, for example.
yeah, so let's just say MA equal to MG. There is only one,
No, forget about MG right now, Rakesh. Sorry, Shajesh.
so it's
Just
just
write
F, you're
F
saying.
equals MA, and you have a one-dimensional
Okay.
case. Okay.
Yeah,
Now you multiply both the sides by dx and integrate. Now you are in a one-dimensional case. You are not bothered about the vectorial, cross out dot, right?
that's what you have in mind.
Yes. Now this dx is an infinitesimal displacement, and that can be written as v dt.
Yeah. So this, you will move this here. We have to go in the calculus
Yeah.
part.
Yeah. So your
So
dx
this
is v
is,
dt.
yeah. Maybe.
Basically, you can write dv by dt as dv by dx and dx by dt, same thing. So this is basically
Yeah.
exactly.
Yeah. So what's the
Okay.
point?
So now this, look at your LHS. It's just a change in kinetic energy. I'm changing some quantity which is quadratic in velocity, right?
Uh-huh.
Half delta k, which is half m v2 squared minus v1 squared.
Yes. Right. So that's final minus initial, let's say.
Yeah, yeah.
Is that?
So now each of this term is a scalar on the LHS because it is quadratic in velocity.
Yes. Yeah. So that's one dimensional. So it is scalar.
So now when
Yeah.
you go to a 3D, so this character that your integral of a force, space integral of force, or line integral of a force in 3D. See, right now you are in 1D, so you didn't have to bother about whether you are dotting or crossing.
Yeah. So you would say this is MA dV by dt. But I can go through the same thing there also.
No, but I'm saying that, no, what I'm saying is that already your experience with 1D taught you that your LHS is a difference of two terms, each of which is a scalar. That's the knowledge that we learned from.
So that's a scalar, I see. So you're saying this is a scalar you want to build. So that's the scalar
that's why you
want to
must
build.
dot your dr here.
Yeah, yeah, but that's more mathematical, right? It's not physical argument. Yeah,
No.
I see what you're saying.
Because
So
each of this
that's-
LHS term is quadratic in velocity, and that's why,
yeah. So
it has
this
to
is
have a
still
scalar character.
this is still half m v dotted with v, right? Is that the point?
Yeah, now this can be now, no, I mean, the rest is just math. Now it is the math. Okay.
Yeah.
But
Yeah.
your argument for dotting dr with f
Even before it is done.
has its origin in your experience with the one-dimensional case, where your delta k, each of this term is scalar, and that's physical. Delta k
But
is
in one
half m.
dimension, you cannot get anything else other than a scale. I mean, I didn't see like how you're motivating this to be a scalar, or maybe I'm missing something. Help me again.
No, he's saying it is scalar because v squared.
No, we know, what I'm saying is we know velocity as a vector, right? We know
Yeah,
that
yeah, but
velocity
this is
a
one
vector.
dimensional now, right? This is one dimensional here, right? So
True.
Maybe-
So, but if the velocity since the velocity has a vector character, and it is quadratic in velocity, okay, then this term would be, 0 here. If we had to cross, each of these two terms would be, comes at the end of the integral half v2 squared. We have to dot v with itself as you. So what will be the, what will be the generalization of this result for the 3D case? Now, can you motivate from here? If you generalize this to 3D, it has to be a difference of Ke, and each Ke term is quadratic in velocity.
Yeah,
And that's why it has to be a
Yeah.
scalar term.
yeah. Like there is this interpretation, right? You can build a coordinate system where, so this is the path of the motion.
Hmm.
So this is dr,
Hmm.
and in your coordinate system itself, you will choose this to be perpendicular direction. Let's say E per. I see. What is it called?
Normal, tangential, and
No.
binomial.
Yeah, exactly. So in that coordinate system, it should come out clear, right? And you said, so Prachi, did you mention that it will be a cross product on the verb direction? I haven't done this, so I cannot.
The normal direction will talk about the change in direction of the velocity.
And Shajesh, physically we know that the LHS is the change in kinetic energy, right?
Yeah, the left hand side is the change in
now,
kinetic energy.
now you
If
see,
we do
Shajesh,
this,
if you have a force which is perpendicular to the displacement, we know from the physics that centripetal forces don't change the velocity, right? I mean, for a perfect circular motion. Okay.
yeah.
So that's why the perpendicular component cannot change the velocity. So the delta K has to come from the component along the motion. Because this is the difference in the magnitude of the speed, right? V1 square minus V2 square.
Yeah, doesn't seem that we are ending the loop, right? It seems like we started from that discussion that why is the perp not contribute, or maybe I'm missing something.
No, because Shajesh, here we proved that the line integral of the force ends up changing the kinetic energy. Okay. And that's why it will change the velocity of the particle. And since the perpendicular component cannot change change the speed of the particle, and since the perpendicular component cannot change the speed of the particle, it cannot contribute.
Yeah, so Rishi, we are back to the same thing that we started with. Like we said that the projection of the force, which is along the direction of the linear motion, is actually helping in the motion, changing the velocity, making it causing acceleration. The one which is perpendicular is only changing the direction of the velocity. That's where we are back to the same thing again. The
No,
one
but
with
Prachi,
the project
to a +2 student, to a +2 student, here we explicitly showed that it is the component of force along the motion that gives you delta K. This is an explicit demonstration of that. We first started with the.
This is just purely mathematics there. Like it is not a physical demonstration of why it is happening. So when you talk about the component of the force along the direction of the motion, that's where you say this is physical. And only way you can construct it mathematically is with the scalar product.
No. The fact that this integral is equal to delta K, which relates to not the change in velocity, but change in speed. That's important. Okay. This is relating it to the change in speed and not velocity, Prachi.
I think what Rishi is pointing out is that this construction is a scalar.
Yeah.
So, I mean, it's, or maybe what
Delta
Prachi is saying, it's not completely.
Speed,
Yeah, like what she's saying is that it's
more of a style of presenting something than it is a foolproof argument in favor of anything.
No, this is, I'm saying that this integral is not change in velocity, but change in speed. That's the crucial physical argument here. That is the change in speed here. For example, in the circular motion, there is a change in velocity, but there is no change in speed. And that's why there is no work done.
But then there is no change in speed either there, right?
Where?
So
that's why
but you can have, it can in circular motion.
That's why there is no work done. In the pure circular motion. The pure central force, the pure, I mean, in the pure circular motion, there is no work done by the.
Yeah. Uniform circular motion. Yeah.
Uniform
There is
circular
no work done.
Yes.
Yeah. Yeah, that is correct. Yeah, good point. So, okay. So, yeah, it is not, I would say I see your point, but I think it's not, I still, it stumps me that, okay, why scalar product? But I think I roughly see it, but at the same time, since I got confused there, yeah, I would say I'm not completely satisfied, but then I get your point though, that this is a scalar, so you would like to build a scalar out of it.
Yes, exactly.
So, yeah, reasonable. Yeah, reasonable. Yeah, yeah. Yeah, yeah, reasonable. Yes. Okay. Yeah, so a couple of good points. I think, yeah, I would especially, I think we should bring back that discussion in the future. So 2 points we left open, I guess. One is this, which is you answered it, but I think it's worth maybe thinking about, for at least for me. And the other is that, yeah, can we do this rotational motion somehow in another point, and can we see the features like what Rishi is pointing out in more detail? Yeah, I think that might be nice thing to do. Yeah, yeah. So okay, so yeah, so any other comments? Sammy and
Just one comment, Shajesh. I'm saying that here,
sure, yes, please.
even in the one-dimensional case, we could see that it's proportional to the change in speed. You know, the magnitude of the velocity, v1 and v2. And
Yeah.
that's a crucial input. You know, that when you go to 3D, it has to be a scalar. It has to be a change. Delta k, if the magnitude remains the same, delta k will be 0. And that's why, and it also confirms to our intuitive understanding that this circular motion, whenever the force is a right angle to the displacement, it doesn't do any work.
I always see this as the main idea here is I feel I at least personally I think that more than it being velocity square, the fact that this is a complete differential, right? So that it depends only on the initial and final point, that is crucial there. It turns out that it is the velocity square that does that job. And then you're saying that, oh, that's a scalar, so do the same thing on the right side,
Shajesh,
construct a scalar.
if it was not velocity squared, okay, then then it would not work out. Okay, because each term could be individually be vector. Okay, but velocity being vector, it has to be dotted with itself to obtain a non-zero individual terms.
Yeah.
Okay, the square quadratic thing is important, because if it was not quadratic in a vector, then
what if I take the cross product, for example, there instead of a dot product with dr, I take a cross product with dr, right? That's a valid thing for me to do, right? So for example, so let's say if I do this, I'll surely get an equation. I'm not sure.
You get the torque equation.
Yes, so this is A is equal to F, and let's say this is A crossed with dr. What is that equal to? So this is dV by dt crossed with, oh, this is 0. Yeah, okay. Okay, so what does that mean? Right, so this is is this 0? Yeah, so this is no, it's not 0, right? This is not 0. This is dV crossed with V, right? Yeah. So that's equal to F crossed with dr. What is this equal to? F crossed with dr. I can always integrate this. V crossed. Yeah, but how does it help me?
So FDR sine of whatever is the angle between them.
So what? What is this? dv
You're
cross?
writing A as dv by dt, right?
Yeah, A is dv by dt. So A
Ah.
crossed with dr is dv by dt crossed with dr. And then, so then I say this is limit, like if this is not satisfactory, so then I say this is delta V by delta T crossed with, let's say delta R. And then move this, at this stage, I can move the T to that side and then take the limit again. So this should be okay. So this tells us that this is dV crossed with V. So that's satisfactory, I think. So that's this. And we can also have total derivative of V crossed with V, which is 0, right? That's dV crossed with V plus V crossed with dV, right? So I cannot use the, or that's not useful at least, right? But that's 0.
Yeah, but you cannot use it.
Can't use it, I said, yeah.
So only way you can use from is basically.
So what if I do the integral now, right? So this is the integral, right? So I go from, this has to go from initial velocity, final velocity, and same thing, our initial, our final, and this time it's along a path. Yeah, this will be path dependent. Yeah. So this is along a path, right? The F dotted with dr, if it was a conservative force, we pretended that that was a conservative, or we did not, right? No, we did not. Yeah, yeah. So
I
this,
believe here your velocity also will start depending on that. That inside will also start depending on which way you are. Because
yes,
every location
yes,
you see
yes.
will have a different
Correct.
behavior.
Correct.
Sorry?
I agree. Because earlier it was a total differential. This is not a total differential. So clearly this will depend on which path you take, right? Or at least it's not clear that, oh, okay, maybe it could be path independent, right? Why do you say this is path
No,
dependent?
but
Is that clear?
even the previous case is path dependent in general.
No, it's not, right? Left hand side.
No.
Uh,
Not the effect, not the effect function.
LHS is of course the LHS, your change in kinetic energy is of course the total differential. That
Yeah.
is of course, but your RHS is of course in
yeah,
general
right
path
hand
dependent.
side, it depends on which force it is. Yeah.
Exactly. Only for conservative forces it is path independent.
Correct. So can we do something? Okay, help me here.
Close the top and continue.
Oh, so Prachi is saying like it is getting too long and should we continue this later? Is that what you're saying? Oh, this is not. This is no. Hold on.
Rishi, this is not what I'm saying. I'm just asking him to stop the recording and we can continue discussing this in between ourselves.
But I thought this was the purpose that we. I mean, this is a good discussion to have, correct? Like I think others can have it. I wasn't that the idea.
But I thought we are like when it becomes too long, people are not interested in going that long.
I agree, but I think this is, I like the discussion and I feel that students might like to listen to it maybe.
Shajesh, what we can do is we can, put a message that typically any talk would be covered in more or less, when people see a 2-hour file, they don't feel motivated to click and open it. So what we can tell is that I think this is what we should typically have, that in all the talks, try and have the main content within the 1 hour, and we can have some discussion there. But if we feel that the discussion is not central to the terminal point, it can be postponed towards after the talk, and then there can be extended open-ended discussion after the talk. So,
I am fine.
Yeah, Basically the same thing, like have a content file not more than 1 hour, and then we can always do a associated video with that, like associated discussion to this file that can go as long as we want.
Yeah, so we can put Shajesh. In fact, I would suggest that,
Rishi.
Shajesh.
Yeah, Rishi, I think it is too early to create laws or restrictions here. I think it's a small crowd. Let it go the way it is. And for now, yeah, we should be constrain the time for sure. Let's be, unless we are extremely excited, maybe we can restrict this and maybe bring back this discussion. Like, how about we bring this discussion, we continue this discussion next time. I don't mind continuing this discussion. Like, we don't have to have a, like, or I can try to do something along this line and then have the discussion next time. Is that going to be productive? You guys like that?
First, maybe we need to work it out, and then once we have some displacement, then we can discuss.
Yeah. I agree. So I will try to do this a little bit. I don't make any promises because I've never done this. So at least make some attempts and have something and bring it on the table here. What do you guys suggest? Do you think that's worth it? That might help? Like, because I think that this might have something interesting. I don't know. Like, it might have been tried, I'm sure. Like everything along this path, someone or the other must have tried. So I'll be surprised if this has never been attempted. Yeah. So yeah, so I say we come back here next time. So is that good enough? All of us think about it, and if we come back here next time, then we continue this. I will orient the discussion next time along this line. I'll start from here. So it'll be hard, but I think I'll do it. Yeah, I'll attempt it. Yeah. Reasonable?
Yeah.
Right. Yeah. Because I feel, I mean, I say that because I would really hate it if we really go along the typical line that, okay, a talk has to be 45 minutes, discussion has to be 15 minutes. I think the point here is that we want to keep it all free in a sense.
Shajesh, see, it's not about the restrictions, but the point is, if you want, see, you, me, and Prachi may be motivated to discuss this, okay? But people who may not be initiated in this, and if you want to, get them along and, give them something to munch upon, to begin with, then if we can structure the talks where, there is a concrete proposition for 1 hour, and then there is an elaboration in the later half. And these two are segregated, then people know that, okay, what is it that they need to get initiated, and what is it, the dessert can be served later, and the main course and dessert can be separated, if there is confusion between the.
Yeah, Prachi says she's for what you're saying.
She's like, Shajesh,
honestly not for it because I mean, it doesn't matter, but yeah.
Shajesh, you think
Yes.
about the books which are written by experts for people who are learning the subject for the first time. They structure it in such a way that more or less chapters either follow, follow in a certain order. And if they think that there is a material required to cover this, and if that material is too demanding, or, it can come in the way they put it in the appendix, right? But there is a segregation.
But I'm saying this is a discussion that came out of the discussion. Like, so, and it is like saying you're walking in a forest and suddenly you see something and you're saying, oh, I don't want to do this. This is not in my plan. I'm not going to explore it. That I think is against our point.
No. I mean, I'm completely with you. I think we are not talking two different things. It's just about how do you organize it. So like, even in the forest, you can have the, main area and a denser area which people can explore. So it's just that mark that this is the, like, in this MTW.
True.
There is a track 1 and track 2, right?
Reasonable. Yeah. Okay.
Just labeling it track 1 and track 2. That's it.
Okay.
Like as Rishi is saying, like we we are trying to make it useful for younger kids also, right?
Exactly.
I mean, they
Yeah.
should be able to see like what is useful for them. And we point out like during the discussion itself, oh, this is an interesting point. Let's come back during the discussion session. Let's come back to this
Exactly.
during
this
the.
point-
Exactly.
For me, forget about kids.
Yeah, but that is not.
Yeah, okay. Yeah, let's not continue. I get your point, and since you guys are 2 in number, and I think unless Sammy supports me, so we are 4 in number, we get 2 + 2 votes. Maybe. Sammy, any comments on how the discussions should be oriented or organized? Yeah. Yeah, it's too late for him. Yeah. I agree. Yeah. Presuming that he's not slept. Yeah. Okay. Yeah, I think let's. I think I'm fine with moderating the discussions or organizing the discussions in a certain way. Yeah. So
Oh,
and
Shajesh,
we'll see.
listen, I'm saying that for every talk, we can have 2 files, the main talk and the discussion part. Why can't we have 2 files?
No,
Let's not have a discussion. Like, this is recording.
Yeah.
This is recording. Exactly the same thing I'm saying, like a student should be having 2 files. We will write it in the description. The associated discussion on this topic is in this file. And give a
Exactly.
link. Give a link
Exactly.
inside the video.
I honestly feel that we are repeating the same curriculum then.
Nahi, Shajesh.
I feel we have to keep this completely free. That's my point of view, but I will accept your point of view because, okay, someone has to give up, right? So I'm ready to give up on that.
No,
But
Shajesh.
honestly, I feel that, I mean, we have to proceed forward, so it's okay to go in a certain way. That's okay. But I'm just saying that why not keep exploring? Exploring is what we are doing, not.
Shajesh, in what way what we are saying is, I'm saying that we want, see, I mean, it's an established fact that, the TED Talks, the duration is 20 minutes, right? Because human
Yes.
attention span is limited. One cannot, if somebody sees a 2-hour file, one will not feel motivated to click. If there is a 50 minutes chunk, one will click on it. And that will hopefully motivate him or her to click on the other 50 minutes part. So it's just, instead of having a 2-hour file, you can have a 250 minutes file. I mean, how does that hurt the cause?
Yeah, it doesn't. Yeah, let's discuss this.
Okay, we can discuss this later.
Yeah, I feel this is style of learning, or suppose. But since we are having a so-called program here, then this thing becomes important, I suppose. But yeah, okay. So I think to keep it reasonable, let's stop here.
Yeah.
Correct? And
Let's go back to that.
let's come back to this discussion next time. I think I will try something along that line. Hopefully I can get something interesting, and I'll bring it up. Yeah. Surely it may not be at least I don't know what the talk is going to be about completely, because I not seen it yet. But okay, I'll get something there. Yeah. Sounds good. Yeah.
Okay. Yeah.
Okay, cool. Yeah, thanks Rishi for all the discussions, and thanks Sammy and Prachi. Yeah, okay, good, nice.
Okay, yeah.
Yeah. Okay.
Yes, I enjoyed the discussion. Thank you.